Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello, everybody. Welcome back to another episode of the A-Level Cookbook. Today, we're going to be doing the AQA A-Level Chemistry Paper 2 from June 2018. So this question's about the reactions of alkanes. Alkanes can be used as fuels. Give an equation for the combustion of heptane in an excess of oxygen. So it's going to be C7H16. We know we're going to be combusting it with oxygen, and we know that it's only going to make CO2 and H2O. So to balance it, we know that there's 7Cs here. There's got to be 7 there, right? We know that there's going to be how many H2s? Well, we've got 16 H2s here, so there's got to be an 8 in front of this H2O. Now, we know we need how many oxygens? Well, it's going to be 7 times 2, 14 for this, and then there's going to be 8 for this, right? So we're going to need 22 of them, but there's 2 in each one of these, so we're going to need 11 there. Done. Now, heptane can be obtained from a catalytic cracking of hexadecane at high temperature. Identify a suitable catalyst for this process and identify one condition other than high temperature. Give an equation for the catalytic cracking of one molecule of this to produce one molecule of heptane, one molecule of cyclohexane, and one other product. So the thing that we're going to be using here for catalytic cracking is going to be zeolite or aluminosilicate. So zeolite. Another thing as well is that we need to use a moderate pressure. So it doesn't have to be really high. It's just got to be slightly above atmospheric. Right, the equation for this is going to be, well, they've told you it's going to be what hexadecane we're cracking. C16H34 is going to eventually start with what you know in the equation first, right? So they've told you that we're definitely going to make heptane, which is going to be C7H16, and then one molecule of cyclohexane, which is same general formula as alkene, so C6H12. So 16 makes up it needs to be made up from these two, right? So 7 plus 6 is 13, so we've got 3 left. So it's C3 whatever, right? 34 minus 16 minus 12 leaves you behind 6. There you go. So alkanes can be used in free radical substitution reactions to produce halogenoalkanes. Give the equations for the propagation steps in the reaction of butane to form 2-chlorobutane. So here, a lot of people just gave ambiguous radicals or just didn't even know where to put the dot. You need to be crystal clear on which carbon atom has that radical when it's formed, right? So if we're making 2-chlorobutane, what's happening is it's a propagation step, whereas a radical is attacking a non-radical thing. So here we're going to start with our Cl radical, which attacks the non-radical thing, which would not have chlorine to begin with. So it's just going to be butane. So CH3, CH2, CH2, CH3, right? Once it attacks this butane, you're going to end up making one of them going to be one of them is going to be HCl. The other thing is going to be something with a radical on it. Because it's 2-chlorobutane, we need to put that radical on the second carbon. So what you end up having is this CH3 CH, this is lost an H now, with a radical on this carbon because it's missing it, CH2, CH3. Lots of people just didn't do that, or they just kind of put it at the end, or they just didn't know where to put it and just kind of hoped for the best and made it very vague. Don't do that. Then what happens is this will then go and attack something else that's a non-radical thing, because that's what propagation is. So then you have CH3, CH radical, CH2, CH3, plus something else that isn't itself that's not a radical, which is chlorine, and is going to make a radical, because propagation is where you radical, non-radical makes non-radical and radical, right? So in this sense, we're going to have to make something that's a radical here as well, which is, remember, a species unbound electron. So it's going to be a chlorine radical plus the CH2CHCl. You see how that radical is no longer a thing now? CH2CH3. There you go. So chlorofluorocarbons are a group of halogenoalkanes currently banned in many countries that cannot be used as solvents and refrigerants because of their effect on the environment, and here's the structure of one here. Identify the radical produced from this CFC that's responsible for the depletion of ozone in the atmosphere and explain with the aid of equations why a single radical can cause the decomposition of many molecules of ozone. So the radical that's the most problematic here is going to be the Cl that's breaking off, right? So it's a Cl radical. Now, some people thought that this came from Cl2, which is not the case. It's coming from the CF, this whole thing here. What this chlorine radical is going to do is it's going to go and attack an ozone, which is O3. We end up with a ClO radical plus O2. That's one of the propagation steps. Remember that propagation is where you have radical attacks non-radical, making a non-radical and a radical. So here, this ClO radical's got to go and attack something else that is also not a radical, which is O3. And what you end up with is you've got your Cl radical back here as well, because it's a catalyst. And then you make 2O2 here as well, like this. So can you see how this is regenerated and it's constantly attacking? And that's what you would say here, is that the Cl radical is regenerated, and as a result, you get a, chain reaction of it, in a sense. Now, you shouldn't really be saying it's acting as a catalyst in a sense, like, technically speaking. What the idea is that you're making more and more of these as the more of these form, and it's kind of a chain reaction sort of thing happening. which means that ozone's completely going down. The reason I just say it's a catalyst just helps me remember, although not technically correct, that this has been remade again almost, if that makes sense. It doesn't really act as one because it's a propagation step. And overall, you don't get, like, that Cl radical back, if that makes sense. It came from something and it will go back to something. So now it says halogen-alkanes are useful in synthesis, reaction pathways shown, so this, whatever, right? So we've got an haloalkane. So you should be able to look at something and immediately recognize what's going on. Halogenoalkane, alcohol, something else happening. You've got something with O2s in it. It's probably going to be from primary alcohol, something with O2s, most likely carboxylic acid. Some other reaction, we get compound Z. Fine. Now, it says give the IUPAC name for CH2, OH, CH3, CH3, CH2, Br. So if we have a look, it's 1, 2, 3 with a methyl on it, right? So that means it's going to be propan something. Now our options are that we have bromo as the thing or an alcohol here, right? The alcohol takes precedence. So this is going to be on the first carbon, so it's propan 1-ol, right? And then what do we have on it? So propan 1-ol, we have 2, right, methyl. So we've got 2 methyl and then 3 bromo. There you go. 3 bromo, 2 methyl, propan 1-ol. So reaction 1 happens by nucleophilic substitution. Explain why the halogenoalkane is attacked by the nucleophile. So a nucleophile, everyone loves saying electron pair donor, but they don't actually just know what the hell they're talking about. Electron pair donor means it's giving an electron pair away. So something with a lone pair of electrons is, happy to donate it. The reason is because it's gonna, if you're thinking about it, the name nucleophile gives it away. Nucleus is positive, phile attracted to. A nucleus, it's attracted to a nucleus, which means it's attracted to something that's more positive, as in it's electron deficient, to give its electrons away. An electrophile, phile means attraction. So like audiophile means somebody who likes audio, sounds, music, right? So an electrophile is something that wants electrons. It's attracted to electrons. Now, in this sense, it's asking you why this carbon was susceptible here. It's because this carbon must be delta positive. It must have deficiency in electrons. If we zoom in on this between its C and a Br, each line is a covalent bond with shared pair of electrons, right? But this Br is dragging it to itself a bit more like this. So that becomes delta negative, that becomes delta positive. The only reason that is because this is more electronegative. So then if that's more electronegative, then this is electron deficient, which means a nucleophile is going to go to town, right? And that's exactly what we're going to talk about here. So a lot of people just kind of struggle to say the comparison with electronegativity, and then they just kind of said, nucleophiles are electron pair donors. What are you doing? That doesn't explain anything, So don't do that. So here, what we would say is that Br is more electronegative. Obviously, you write the whole thing. And therefore, carbon is partially positive. So then the lone pair on a nucleophile is donated to the delta positive carbon. That's the only reason why it wants to go for it. Otherwise, it's pretty happy existing as is. The infrared spectrum of compound Y shows a significant absorption in the range of this. Draw the displayed formula of compound Y. So if we have a look at compound Y, we've got C4H6O2, right? So I initially was like, oh, it could be a carboxylic acid. Now it's changing because I now know what its IR spectrum is, and I'm no longer thinking that. Instead, what I'm thinking of is that this peak is just C double bond O, but it's not told you anything about an O and an H. So in this case, there's no OHs in this. It's got to be something with 2 C double bond O's in it. If that's the case, it's going to be, if we look at compound Y, 1, 2, 3, and then remember this initially started off as a branched meat thing. So 4, right? H, 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 and the C double bond O, which I picked up from the data sheet, but I don't have it here because I just, just go get it yourself. It takes ages to copy and paste. Trust me, this whiteboard is terrible. And then, yeah, that's what it would be. So then it says compound Z has the empirical formula C3H4NO, give the structure of Z, and then suggest a reagent for this. So we need to think about what's happened between between here to here. Something has caused it to start picking up ends. So in your head, you should be thinking of that big synthetic pathway and being like, what's going on here? We now have what looks like, this aldehyde thing going on, eventually having nitrogens in it, right? What's probably happened is we've got a hydroxy nitrile. That's the route we can go with that. So what you end up with is you end up having the same thing as before, the C, right? With our H, H, and now CH3. However, the aldehyde will have been reduced down into an OH, so there should be an H there as well, and this will go down to an OH, that's the hydroxy part, and then nitrile is because it's got extra carbons in, CN and NC. Sorry, CN. Now, another key thing here as well is that this is empirical formula C3H4NO, right? That's C4H6, that's its actual formula. The empirical formula of that is going to be what? C2H3O, right? 3 and 4 are not multiples of each other, so clearly the carbon chain must have changed in length as well, so that's another hint to me saying that there's a nitrile stuck in this. Then the reagents that you would use for this is what you're going to put in this reaction, which is going to be KCN and dilute acid. There you go. So the oxidation of propan-1-ol can be from propanal and propanoic acid. The boiling points of these compounds are shown in this table. So here's the boiling point of propan-1-ol here. And just as a reminder, draw what the group looks like if it helps you. COH, right? That's what an alcohol looks like. Propanal is an aldehyde. All aldehydes look like this. There's no just double bond on its own because ketones have that as well, and also carboxylic acid to make it crystal clear that it's that. Propanoic acid, C double bond O, O, H. Boiling point is highest for you. It's kind of high for you, and there's the lowest for you. Cool. In the preparation of propanal, propan-1-ol is added dropwise to oxidizing agent. The aldehyde is separated from this by distillation. Explain with reference to intermolecular. Inter is between molecules forces, why distillation allows propanal to be separated from the other organic compounds in this reaction mixture. So some people were talking about things to do with breaking bonds within molecules as in covalent bonds. That's incorrect. If you're breaking covalent bonds, we're not boiling something, we are physically breaking it into two. So I2 would be II, for example. When you're boiling it, you're not turning it into singular I atoms. You are breaking bonds between the molecules, which could, in this case, are van der Waals. So here, what we need to talk about is we need to describe all the forces between them. So we have a look at aldehyde, the propanal, right? So the propanal only has dipole-dipole interactions or forces, and it has got van der Waals as well. But this isn't the differentiator. The key features is that. Whereas your propan-1-ol and your propanoic acid have hydrogen bonds. Can you see an OH and an H there? So it's got hydrogen bonds. Therefore, there's more energy needed to overcome hydrogen bonds because they're stronger. Therefore, aldehydes have a lower boiling point, so they can be distilled because they evaporate first. That's all it's asking you to do. Now it says, give 2 ways of maximizing the yield of propanal obtained by distillation of this reaction mixture. What you want to do is you want to maximize propanal, but you don't want all the other garbage, right? So we need to make sure it's only at the boiling point of propanal and not all the other ones. So you can see here, this is 97. We need to keep this temperature below the boiling point of at least 97. So keep the reaction mixture temperature below the boiling point of the other stuff in the equation. So for example, you should really refer back to this in this example. So below the boiling point of propan-1-ol, or for example, just saying the temperature at which it boils as well. Either's fine. Now the other option as well is that you can then just, what we also should do really is cool the distillate using a condenser, because then we'll collect all, then we won't evaporate more of it and lose after as well. So now it says, describe how you do a simple test tube reaction to find out if this propanal obtained by distillation doesn't have any propanoic acid. Carboxylic acid, one simple test tube thing. The only thing you can do here to get rid of this, to determine whether it's propanoic acid, is by adding a metal carbonate. So for example, add CaCO3, and it would effervesce or bubble if the propanoic acid was present, because it's making CO2. Other people were talking about testing for an aldehyde by adding 2,4-DNP or like tolerance reagent. That's not correct. They're looking for propanoic acid. So now a student carried out an experiment to determine the enthalpy of combustion of ethanol. Combustion of this much increased the temperature of this by this. Calculate a value in kilojoules per mole for the enthalpy of combustion of ethanol in this experiment. Give your answer to an appropriate number of significant figures. So a lot of people just kind of did not do, they didn't use the common sense. They didn't put a negative sign in. They didn't put the number of significant figures. Some had just jumped to doing some other random stuff for some reason. The formula we're using here is we're combusting this much ethanol and we're increasing this much temperature. So we're going to be using Q equals, and it's even told you here is what C is, MC delta T, where that's your energy release or absorption, whichever one it may be. So it's really the energy change, right? This is the mass of the thing having the energy change, not the substance. It's the mass of the substance heat, receiving or losing heat. C is the specific heat capacity, and then delta T is your temperature change, right? So work out step by step. So delta T is going to be your final temperature minus your initial. So final minus this, 40.2 minus 25.1. If we do that, we get 15.1 Kelvin, degrees Celsius, whatever you want to call it. It still works because they both go up in the same increment. Fine. So that's delta T dealt with. The M is the mass of the thing that's either gaining or losing heat. Here, it's 150 grams, not the mass of the ethanol. Delta T, that's fine, and C is that. So then the heat, and this, has gone up. This temperature's gone up, so it's a negative. It's exothermic. So that means that the energy change is going to be Q equals MC delta T, 150 times C, which is 4.18 joules per Kelvin per gram. So that's MC times delta T, which is 115.1. If we do that, we get 9467.7 joules. But remember, we want it in kilojoules per mole. So we're not done, because that means you now get 9.468, we'll round it, kilojoules. Still not done though, because the question's asking you in kilojoules per mole. When we're measuring enthalpy changes, we're measuring enthalpy changes in terms of the kilojoules, the energy released or absorbed per mole of substance. So in this question, this technically is saying that, how much ethanol did we use, sorry? 457 milligrams. If I change that to grams, 0.457 grams burnt, released 9.468 kilojoules of energy. So you could say that's 9.468 per this many grams of ethanol, right? But they want it per mole, not per gram. So what we need to do is we need to work out the moles of ethanol that we had here. Our moles of ethanol is just going to be 0.457 mass over its MR, which is 46. So that's 9.93 times 10 to the minus 3. So then 9.93 times 10 to the minus 3 moles led to a release of 9.468 kilojoules. If I had double this, then obviously I would have double this, right? So then therefore, 1 mole of this, you're dividing this by this, must release 9.468 kilojoules divided by the MR, so the moles, 9.93 times 10 to the minus 3. If we do that, we get roughly 953 kilojoules per mole. 1 mole releases this much. However, it's exothermic, so we need to include a -2. That's how you do it. So a mixture of isomeric alkenes is produced when pentan 2-ol is dehydrated in the presence of concentrated sulfuric acid. Pent-1-ene is one of the isomers produced. Name and outline a mechanism for this. So the mechanism here is we're booting out water, so it's elimination. A lot of people got confused in this question and started talking about elimination in terms of like halogenoalkanes and stuff. That's not what we're doing here. Number one is when you're drawing mechanisms, think about where the electrons are going. As in, don't just draw curly arrows and memorize them. Think with your brain a little bit. Trust me, thinking's good for you. Here, what we're starting with is we're starting with an alcohol. So we've got a COH, and eventually we're going to make an alkene, which is C-double-bond-C. So a good start is to draw what you definitely know is going to appear in this. So here then, we've got CH3, CH2, CH2, C, CH3, H, and then an OH, right? Now, in an alkene, there is no oxygens on it, right? So we need to figure out a way to boot this off. What happens is that the reason we're adding this acid is because an H plus comes along. And H plus is like, la-di-da-di-da, I want electrons. And this oxygen's like, hey bro, I got lone pair of electrons, you want to try and get some? And what happens is it gives the lone pair of electrons to the H plus, right? What you then end up with is you've got the CH3, CH2, CH2, C, CH3, H, O, H2, plus it's giving away more electrons than it wants. Now, this is a problem because oxygen's like, hey, bro, I got not enough electrons. I need some more help, right? So the only solution it can do is nab them from this covalent bond here like that. So what this does is this bond breaks. And that boots off the oxygen too, which is a good thing because we don't have oxygen in our end product. But what we end up now with is we've got CH3, CH2, CH, C, CH3H, and then a plus there. We're stuck because this carbon's now not got enough electrons, although we have booted out our water. Now the problem is the carbon's like, I need to figure out what's going on, and if you look as well here, it's an alkene, so we're eventually making a double bond. So what happens is that if we, something else has got to boot off electrons and something like that, to first of all get enough hydrogens to, fit the alkene, but also to give us a nice double bond, a nice rich one here. So what happens is one of these hydrogens is booted off. Now you wouldn't draw the arrow like this because that would give you H minus, let's say the electrons are going there. We're booting it off somewhere. What happens is this hydrogen's booted off and it gives its electrons to this here, which makes it a double bond. So then what you end up with is CH3, CH2, CH, C, double bond C, H, H, like that, 1, 2, 3, 4, that's all that, and then plus an H2 out there like that. So just think about it in the common sense way, if that makes sense. You're going to have to boot off this eventually and make a double bond. This is how. A pair of stereoisomers is also formed. Name the less polar stereoisomer formed. Explain how this stereoisomerism arises. So if we're looking for what's less polar, well, first of all, let's have a look what we're making. 1, 2, 3, 4, 5, right? It's pent-1-ene or pent-2-ene. So pent-2-ene. But remember that the double bond doesn't necessarily have to be between these two. It could also be between, because you can see this is the original carbon, it could be between here or here. So what you can end up with is pent-2-ene instead. So the one that's more polar, generally speaking, is the one that's cis isomers or Z isomers. It's the same side. They tend to be polar in most cases. Whereas E ones, the opposite sides, tend to be less polar. The way I like to think of it is almost like, imagine you've got this here, like a plus, negative, right? That's not really technically what it is, but like this is how it makes sense to me. Here you got plus and negative, right? The overall plus is on one side and there's another one here, right? They're the same side. Whereas if I have a plus and a plus here and the negative here, can you see how they almost like cancel out and there's no overall thing? Not that that's necessarily true here, but that's how I remember this. So here, the thing that we're going to make is the opposite side pent-2ene, so E pent-2ene or trans pent-2ene. And why is it that we get, first of all, explain how this stereoisomerizes. Number one is that the C-C bond cannot rotate, and it's asking why this type of stereoisomerizes and why this one comes along. But that doesn't do it. That doesn't tell us enough about why stereoisomerism is, because if it was here, these can't rotate, and that still doesn't give you stereoisomerism. What it is that each carbon has to have two different groups, which is why that can't be a stereoisomer. So here we would say each C atom has two different groups. There you go. So compounds A and B react together to form an equilibrium mixture containing C and D. A beaker contains 40 centimeters cubed of 0.16 mol per deciliter cubed aqueous solution A, 9.5 times 10 to the minus 3 moles of B, and 2.8 times 10 to the minus 10 to the minus 2 moles of C were added to this beaker, and the mixture was left to reach equilibrium. The equilibrium mixture had this much A. Calculate the amount of B, C, and D in this equilibrium mixture. Lots of people didn't get the marks in this because a lot of people just kind of went straight into saying, oh, well, this must be this, mole ratio, blah, blah, blah. Like, dude, it's 5 marks, dude. It's not going to be that easy. Like, come on, you're not suspicious? And also, as well as that, think about it common sensively, use what the question's telling you. They mixed these two together. Chemistry is all about how things interact with each other, like the molecules and atoms and this and that, blah, blah, blah. That's what it is. They've mixed these two together, and they've also added a bit of this. These two are going to react with each other to make this, and their numbers are going to go down. And then these are going to also react with these, and their numbers are going to go down to make this again. And eventually, it's a back and forth until you hit equilibrium. When you're first mixing these together, it's not in equilibrium. They need to keep backing and forthing until it's equilibrium-y. So what you need to do is you need to work out what the equilibrium amounts of all of these are. Whenever you have any, and this applies to like acids and bases as well, the same principles. So, and Kp, and K, literally anything in the universe. So what we need to do is we need to first of all write out our equation separately again here, like this, and make a little table of what's happening and think about it logically. So what I always recommend doing is this. So you would do the moles before your equilibrium, just when the moment everything's mixed, and then your moles at equilibrium. Some people like to put a change in the moles. I just kind of don't like doing that. Like, why? That's just too much mess, personally. But you can do it if you want. So we need to work out the moles before the equilibrium for all of these things. Read the question and the context carefully. So beaker contained this much of A. Well, it's just giving you the volume and concentration. So that means the moles before the equilibrium was going to be 40 over 1,000 times 0.16, right? So the moles of A at the start must have been 6.4 times 10 to the minus 3 moles. Now, this much moles of B was added. So again, this is before the equilibrium's hit, just when it's been added. So 9.5 times 10 to the minus 3 moles. And then as well as that, they added this much C. So then there must have been 2.8 times 10 to the minus 2 moles. Don't assume that this is just 0. The question's told you that some has been added. D, there is no D here. So when you're first setting this up, none of this has been made yet. Now it says it's been left to reach equilibrium. Now when equilibrium has been reached, it told you that there was this much A. So now at equilibrium, we will write 3.9 times 10 to the minus 3 moles of A. So what we now do is we compare what happened to A, and then the rest will follow. These two will again react and drop to end up making these which go up. So if we compare what's happened between here and here, A has dropped by what? 6.4 times 10 to the minus 3 minus 3.9 times 10 to the minus 3. A's dropped by minus 2.5 times 10 to the minus 3. Okay? Every two of these needs one of these to react to then make three of these and one of them. So if this is dropped, if we needed two of these to go, then a half of this many's got to drop. So in this case, it's going to be a half of the 2.5 times 10 to the minus 3, right? So it's going to be 9.5 times 10 to the minus 3 minus a half of that. So minus a half of the 2.5 times 10 to the minus 3, which means the moles of the B at equilibrium was 8.25 times 10 to the minus 3 moles, right? These will have dropped to then make these. So if this many went down, then some amount of this has gone up and this has gone up, okay? So two of these makes one of them. So if two of these dropped, one of these were made. So that means it's going to be, in this case, minus 2.5 dropped is going to be plus a half 2.5 times 10 to the minus 3. If that's the case, what we end up getting is we get 1.25 times 10 to the minus 3 moles of D. All right, cool. And then here, this is where it gets a bit juicy. One of these made three of these. So if three lots of this dropped, 3 lots of this were made. So this is going to be 3 lots of this one, or you could do 3 lots of a half of this one. So it's going to be 3 lots of a half of 2.5 times 10 to the minus 3. Now if we do that, we end up getting, so remember we're adding this onto the 2.8, 0.03175 moles So then the equilibrium amounts of each of these is what we've just gotten there. So the amount of B was, 8.25 times 10 to the minus 3. The amount of C was 0.03175. So I'm going to stick to the number of significant figures in the question, so 0.0318. And the amount of D is 1.25 times 10 to the minus 3. Now it says to give an equilibrium expression constant Kc for this and its units. So it's going to be these. So its products, the concentration, because it's Kc, so it's going to be C cubed times D, concentrations, all over A squared times B, right? Now, it's saying its units as well, right? So these are concentrations. Moles per decimeter cubed times moles per decimeter cubed to its 1. What you're going to end up with is you're going to have mole dm minus 3 to the 4, all divided by mole dm minus 3 to the squared times 1, 3. Which means you're left with these, this cancels out, and you're left with one of them. So then the units are just going to be mole dm minus 3. So different equilibrium mixture of these four compounds at different temperature had this much of the B, this much of C, and this much of D in a total volume of this solution. At this temperature, the numerical value of Kc was that. Calculate the concentration of A in this equilibrium mixture and give your answer to appropriate number of significant figures. So the question is saying that it's still running this same sort of equilibrium reaction, it's just we've put different things in it in different temperatures. So we need to rearrange this to find what A is. So first of all, I'm going to rearrange that by multiplying both sides by A squared and then moving the Kc down there. So then I can say the concentration of A squared is going to equal C cubed times D, all divided by Kc times B. So then that means I can just go one step further and say, well, if I want A, then I'm going to square root this whole thing, like that. If that's the case, then the concentration of A is going to be the square root of the concentrations of all of these things. Now, the issue here is that they've given us the moles of everything and not their concentration. So real quick, we're going to have to work out the concentrations of all of these bits and bobs. So B, C, and D, right? So in B, they told you it was 0.21, and it's over 5 times 10 to minus 2 centimeters cubed. Sorry, 5 times 10 squared centimeters cubed of solution. So if we change that to decimeters, it's going to be 0.5, right? And then this one's going to be 1.05 over 0.5, and then that's going to be 0.076 over 0.5. If we do that, we end up getting for each of these 0.42, and then 1.05 for the 1.05, we're going to get 2.1. And then for the other one, it's going to be 0.076 over 0.5, which gives you 0.152. They've told you in the question Kc was 118. So to then put all of this in, it's going to be 2.1 cubed times D, which is 0.152, all divided by Kc, which is 116, times the concentration of B, which is 0.42. If we do that, then the concentration of A must equal 0.16998, which is roughly, we should put it to the number of significant figures of the question generally, which is going to be 0.17. There you go. So it says, justify the statement that adding more water to this equilibrium mixture will lower the concentration of A in the mixture. If you have a look, A is dependent on the square root of the concentration of all of these things, right? If I add more water, what's happening is, if we look at each component here, these are going to get more dilute. So that concentration is going to drop. That concentration is going to drop. That concentration is going to drop, right? This is a temperature, though, that is fixed. The only thing that affects Kc, Ka, K, anything in the universe, Kp, is temperature. So this number has got to stay fixed. So what it will do is this equilibrium will shift about till that Kc stays the same, as in things will go down and up. So if the concentration's dropping of all of these things, what's going to happen is the equilibrium is going to try and increase the concentrations of all of these by making the moles go higher in each of those things. So what ends up happening is that the equilibrium will shift towards this way to increase the number of moles of this and this, which will then put the concentrations back up respectively, as in it will move to the side with more moles. So to put it into words, I like to think of it as, well, here's the change you made. The equilibrium will try to shift to counteract the change, but don't say counteract the change, say what the change is, right? Because a lot of people are just poorly, unable to answer this. 65.8% of people couldn't answer this question. So what happens is immediately the change, so when you say change and oppose the change, say what the change is. The concentration of all substances in this, A, B, C, and D, and so forth, decreases due to the dilution. So then what happens is the equilibrium shifts to increase, as in say what the counteracting the change is, the change that's being counteracted. So it's going to shift to increase the concentration. And how it does this is by shifting to the side with more moles, because mole concentration equals moles over volume. If we've put the volume up to keep the concentration back to normal, we're going to have to get this to go up as well to negate the effects of that. There you go. So here it says bromate ions and bromide ions are in this react in this acidic conditions. A series of experiments are given at temperature, and they've got this rate equation. Here's some incomplete data. Use the data from experiment 1 to calculate the value of the rate constant K, and then give your answer to the significant figures. So what we've got to do is we've got to look out for an equation and use that rate equation to find out what the value of rate constant is. They've told you the rate equation here is this. So we know that the rate equals K times all of this, right? So if I want K, it's going to be rate divided by this whole chunk. So the BRO3 minus the BR minus and the H plus squared. If I do that, I need to just pick one which has all of those bits and bobs that we need. So it's going to be here, for example. So we would do 2.4 times 10 to the minus 2 divided by the concentration of BR3, which is here, 0.1, times BR, 0.2, times 0.3 squared. Now if we do that, we get roughly, well, it's got to be two number of significant figures that matches the question, so 2, so I'm going to go with 13. Now to work out its units, all rates in this context are going to be measured in mole dm minus 3 s minus 1. And also you can see that because the table tells you this. Now we're dividing it by concentrations that have been multiplied by each other, 1, 2, and then squared. So the power of the bottom fraction is going to be mole dm minus 3, no s though, it's the power of 4, like this, right? This is going to cancel out and you're going to be left with 3. So now what you've got is think of that as like a 1, right? So it's going to be s minus 1 over mole 3 dm minus 9. If you're putting over, what that means is that basically, for example, if 2 to the minus 1 is going to be 1 over 2 to the 1. So here, we need to turn this into units that aren't just like a fraction. So the units are going to be mole minus 3 dm plus 9, so just 9, s minus 1. So now it says complete table 2, and here's some space for working. So we need to find out the initial concentrations of all these things are. Right? So for BRO, we need to rearrange this equation to get BRO on its own. So in that case, all you do is you just rearrange it to get the BRO concentration. So BRO3 minus concentration would equal your rate divided by K, BR minus NH plus squared. So it would be the rate of this equation, which was 2.4 times 10 to the minus 2, divided by the K we just got, so 13, times the BR minus, which is 0.2, times the H plus squared, which is 0.3 squared. If we do that, we get... Remember, number of significant figures is 2, so we're going to stick to what they use, so it's going to be 0.15 there. Cool. So then for the other one, all you need to do is just slap into the rate equation with your K. So it would be K, which is 13, times BRO3, which is 0.2, times 0.4, times 0.5 squared. If we do that, we end up getting 0.26. Cool. And then for the last one, you just rearrange it by doing rate divided by this, divided by this, divided by this, and then square rooted. Just for sake of time, I'm going to skip ahead on that because it's just going to take too long, so it's 0.46. There you go. For this question, you can see there's a quick shortcut you can take from here as well. As you can see, that's first order. So here, these are the same, those are the same, but the rate's gone up by something. Can you see how it's gone from 3.6? Sorry, it's gone from 2.4 to 3.6. So if you divide by the two of those, you can see that this rate is times by 1.5. So therefore, the concentration of this BR must have gone up by times by 1.5 as well. So here you can work that out. That'd be 0.15 there. Now here, in initial rate of reaction, you can see what's changed between each experiment. So from here to here, that's been times by 2. From here to here, that's times by 2. From here to here, that's gone up by a factor of what, 0.5 to 0.3? So it's gone up by times 5 over 3. So the rate will have gone up by, you would times the rate by 2, because it's first order, and then here times by 2 again, because it's first order, and then times by 5 over 3 squared. If you do that, you get 0.27. Then for the last one, if you see here, the rate's gone up by some sort of factor. So again, 2.7 by times 10 to minus 2 divided by 2.4 times 10 to minus 2. This has gone up by times 9 over 8, right? This has stayed the same. This has been times a half. This has gone times by something. So a half times something squared, gives you 9 over 8. So then x squared has got to be 9 over 8 divided by a half. So if I do 9 over 8 divided by 1/2, I end up getting 9 over 4. So that means x, whatever mysterious number this is that they times it by, has got to be the square root of this, which is 3 over 2. So this thing's been times by 1.5 or 3 over 2. So that means if we do 0.3 times 3 over 2, we end up getting 0.45, like that. That's a quick shortcut way of doing it. So second series of experiments is carried out to investigate how the rate of reaction varies with temperature. The results were then used to obtain an activation energy value, and identical amounts of these were done, and they ran them at different temperatures, so forth, and it says complete table 3. So this is temperature, that's 1 over temperature, so you just do 1 over 302, which is going to be some sort of thing. We want to stick to the same number of significant figures, so it's going to be 3.31 times 10 to the minus 3. Then if we have a look here, that's whatever, and it says ln 1 over t. So you're just going to do ln on your calculator, this number here. So if I do that, we end up getting minus 3.30. Cool. The Arrhenius equation can be written as this. In this experiment, the rate constant k is directly proportional to 1 over t, where c1 and c2 are constants. Use the table values of table 3 to plot this against the graph, and then use your graph to calculate a value for the activation energy of this, and the value of the gas constant is this. So basically, you plot your graph, whatever, right? I'm just going to copy and paste one just because I'm going to why would I do that? It's going to take too long. Cool. So we've got a nice, lovely graph here, right? You just plot it like that. And it says it wants your activation energy, right? So they've given you this here. Look at what they've done and compare it side by side. I don't think it's very useful, memorizing like equations. And also I can see from this as well, a lot of people just kind of jumped into doing, some sort of calculation and this and that, and blah, 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 right? They've told you that they've plotted this, and you can see on the axis, it's ln 1 over t here equals all of that. So if I rewrite, if I put ln 1 over t equals minus ea over r 1 over t plus c2, that's what we've got. Your y-axis is here, your x-axis is this. Now, every single straight line in the universe will follow y equals mx plus c. Every single one. Where y is the y-coordinate, x is your x-coordinate, that will give you the y, m is the gradient, and c is your y-intercept. So what all you need to do is compare your graph to this. So in our graph, our y has now become 1 ln 1 over t, and our x has become 1 over t, like this. All right, so then what we do is we rewrite y equals mx plus c in the ones we have now. So our y is now ln 1 over t, and that equals m, the gradient, we still don't know what that is, times 1 over t plus c. Now compare this to what they've given you. This matches, this matches. Can you see the 1 over t here and the 1 over t's here? Can you see how that must be m then? M. So m in this example must equal ea over r, and that c2 is also the c here as well. So if the m is ea over r, that means our gradient equals minus ea over r, because that's what m is, right? And now we're getting a step closer. So to work out the gradient, all you've got to do is pick 2 points and then work out the difference in y and the difference in x, right? So I'm going to try and pick coordinates that look like they align pretty nicely as best as I can. So if I go for here, and then I go for here, right? Now the gradient is y2 minus y1 over x2 minus x1. Now a lot of people make this mistake and it's really annoying. This is your second coordinate, that's not. A lot of people would choose this one and say, oh, it must be this one minus this. It's not. The further to the right you go, because we read left to right, is the further the coordinate is. So this is your second, that's your first. Even if it's going down, even that gives you a negative number. And it should give you a negative number because it's a going down graph. It's a negative graph. So the gradient here is going to be our second y coordinate. So if you see the scale here is hideous. So that's going to be what? That's going to be like minus 3.34. And then it's going to be minus the next coordinate. So where's our next? So our first coordinate here, which if I just try and work out now, is going to be minus 2.68. And don't worry about double minuses and all of that stuff, because these are in minuses. You're supposed to be doing that. That's what I'm going to take at face value. So second x coordinate, which is going to be the 3.4 times 10 to the minus 3, minus our first x coordinate, which I picked was here, sorry. So it's 3.3 times 10 to the minus 3. Now if I do that, we get a gradient of minus 6600. Right, and that's right. It should be a minus because it's going down. Cool. So if we come back here, then we know that the gradient is minus ea over r. So we now know that minus ea over r is equal to minus 6600. So that means minus ea is going to be this times 8.31, right? So if we do that, we're going to do this times 8.31, which gives you minus ea of minus 54846. So then ea is going to be 54846 joules per mole, because the Arrhenius equation only works if the activation energy is in joules per mole. So we want it to be in kilojoules per mole, so it's actually going to be this divided by 1,000, but we need to stick to the number of significant figures in the question, so I'm going to go with 54.8 kilojoules per mole. There you go. Can you see that's positive? So that's why I got to stick to the gradient, because a lot of people ended up getting the wrong numbers and bits and bobs as well. They allow a range of 54.0 to 56.5. Data about the hydrogenation of cyclohexene and benzene are given. So here we go. We have one alkene group here. We hydrogenated, its enthalpy change for one of these hydrogenations is minus 120. And we got benzene, and if we do 3 lots of hydrogenation, it's that. So now it says explain the bonding in and the shape of a benzene molecule, and compare the stability of benzene with that of a hypothetical value, and then use the data in your answer. So let's talk about the bonding number 1 first in benzene. So in benzene, so try bonding. What happens is that you've got those 6 carbons, right, chilling. 1, 2, 3, 4, 5, 6. And they've got their p orbitals floating around like this, right? Now what happens is 3 carbons out of each of them are bonded with each other, but they've got spare electrons floating around in these p orbitals. So what happens is they overlap like this. So you end up getting a ring above and below the benzene, like that. And that's your pi cloud. So what happens is each carbon has 3 covalent bonds, and one, the other electron's not doing anything, chilling, it's delocalized electron. Now this delocalized electron arises because these spare electrons overlap overlap in their p orbital. Sorry, their spare electrons p orbitals, I should say, for each carbon overlap, and this forms a pi cloud or ring, a delocalized ring, and that's what gives them delocalized electrons. Cool. So then it says that's that bonding done. We need to talk about the shape. So the shape here then is that it is planar. It's a planar hexagon, and in benzene the bond angles is just stuff you got to remember. Unfortunately, the bond angle is 120 degrees. And the other thing about benzene that differs from the other stuff is that the CC bonds are all equal in length, whereas in cyclohexene they'd be different. We looked at this with X-ray crystallography and found that they were all the same length. So CC bonds are all same length. All right, cool. They're actually a length in between a single and double bond. So then that's that bit done, and then it says compare the stability of this. So in terms of our stability, we need to look at the numbers they've given us, right? So in order to cause hydrogenation of one double bond here to eventually get this, it needed minus 120. Now we used to the Giese-Kekule proposed that like there were just 3, double bonds in this, right? So we would expect the delta H of hydrogenation to be 3 lots of that one, right? So, and that's what it also hints at the question as well, that'd be expected of this, right? So here, 120 was for one of them, 3 of them is going to need that. So the expected delta H of hydrogenation of the cyclohexa blah 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 triene, right, would be 3 times minus 120, which is minus 360 kilojoules. But the actual one, can you see how it's minus 208? The actual hydrogenation enthalpy for benzene is minus 152 kilojoules per mole, right? Can you see how that's less exothermic? It's more positive. So benzene is less exothermic when you're doing this. Therefore, there's less energy released when bonds made, because bond making, remember, is exothermic. Bond breaking is endothermic when bonds are made. Therefore, what happens is you what was the word I was going to say? Oh, therefore it's more stable. Sorry, whoops. That's it. There you go. So now it says the enthalpy of hydrogenation of cyclohexyl-1,3-diene is not exactly double of that cyclohexene. Suggest a value for the enthalpy of hydrogenation of cyclohexyl-1,3-diene and justify your value. So what we need to do is we've got to have a think. What could be going on? What you would expect it to be, remember that we just want to expect it to be, would be what? Minus 240. If it's 2, right? Minus 240. But for some reason, it's not. And the question just told you that. So we need to think about what could be going on. Now, if we've got hexa, what was it? 1,3-diene, right? There's 1. There could be 3 here. You need to just, the only thing that you can think about, like, is that you got to compare the differences fundamentally, really. So what I mean by that is between this versus this thing here now with the double bond in, the only difference is that there's double bonds separated by a single bond, which could be an explanation as to why that might be, that might not exactly be a double. The reason is because there's these double bonds that are separated by a single bond, you can actually have some overlap of these p orbitals and some delocalization. So what happens is this actually becomes more stable in that sense. So as a result, it's actually less exothermic. So it would be any value between, minus 240, I guess more positive than minus 240, but not so positive that it's above 121. So I'm going to go with I don't know, minus 220 or something kilojoules per mole, as in it's between minus 240 and minus 121, minus 239, right? And the reason is because, the fundamental difference is that there's double bonds separated by single bonds. And as well as that, you can see that the reason that this wasn't too, happy and was more stable was because of the fact that there was some, that these are p orbitals are delocalized or they overlaps. In this case, there's probably some happening here as well. So this must allow some overlap of p orbitals or some delocalization. There you go. So acyl chlorides, remember an acyl chloride always looks like this, C double bond OCl, and their derivatives are carboxylic acid, so they can do some similar reactions. Reagents in synthesis, they react with aromatic compounds. These are benzene containing and also with alcohols. So CH3CH2 COCl reacts with benzene in the presence of AlCl3 and electrophilic substitution, Give an equation for the reaction of this to form the electrophile, and then outline a mechanism for this. So it's electrophilic substitution. Electrophile is something that is attracted to electrons, and the electrons it's going to go for is in the benzene ring. And substitution means it's swapping for something, right? The swapping is going to be it's swapping for a hydrogen in there. So first of all, it says outline the mechanism for the reaction with this to form an electrophile, right? So what we do is we have our CH3, CH2, COCl. Always write down what you know first. The question's told you that it will react with AlCl3 to eventually give you an electrophile. Now, an electrophile, if it wants to accept electrons, it itself has to be deficient in electrons. Now, if that's the case, this carbon here is the one that's becoming deficient, as in it's booting something off. If it does, this is getting booted off. So what you end up having is you have CH3, CH2, CO with a plus on it now, and now we've got this Cl minus, which bonds here. So you end up with AlCl4 minus. That's your electrophile. It's hungry for electrons. So in this mechanism, what happens is, first of all, we've got our nice lovely benzene. Remember that the arrows are the movement of electrons. So we've now got this CO, CH2, CH3, but remember that's positive. It's an electrophile, so it wants electrons, and it's attracted to the benzene ring. So what happens is electrons from the benzene ring go this way. That's why we draw the arrow that way. Then what happens is, because whenever you draw this, you've now made a bond, right? It's now bonded to this COCH2CH3, right? But the issue is that it's giving away electrons from its beautiful ring. This doesn't give it any in return. So this benzene ring is now stuck. Remember that there's also an H here. It's also got too many bonds. So it's like, I need to fix this somehow. The only option it has is to boot off the H that was already there. Remember that there's always H's on all of these? So then what happens is, by booting it off, we don't do this because that means it's giving an electron away to this. You'd get an H minus and then a 2 plus here. We don't want that. We need to put electrons back into the system, so this bond breaks like that. As a result, what you end up with is now you've got your happy little benzene chilling again with its enough electrons in there to be happy, and it's got its COCH2CH3 like this, right? And then, as well as that, you've also got an H plus. That H plus will then react with the AlCl4 minus, and it will regenerate AlCl3, hence a catalyst, and it will also make HCl as a byproduct. The organic product in question 0.71 can be converted into this alcohol shown. Give the IUPAC name of this alcohol, then write the reagent needed for this and name the mechanism. So first of all, let's have a talk about what the actual name of this thing is. So here, because it's got a benzene on it, I'm going to go ahead and say it's a phenyl, because it'd be really hard to name this with like something benzene. I just think it's easier to put phenyl, right? So 1 phenyl is what it's probably going to end up being. 1 phenyl, because that's probably the highest priority of all these. 1, 2, 3, right? So propan, 1 ol. So 1 phenyl, propan, 1 ol. Now we need to think about the reagent to get it. So the organic product from the previous question. So here we ended up making this, right? Which is, if you zoom in on that part, it's going to be C double bond O, blah, 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 right? So then, if you have a look, now we've changed it from a C double bond O to an OH, as in we have now reduced that ketone bit there, because we made a ketone before. So what we're going to be using is NaBH4. And the mechanism by which it does that is that we're adding on an H, and the reason it's getting added on is because we add an H minus, which has a lone pair of electrons, so it's nucleophilic addition. There you go. So the alcohol shown in this question reacts with ethanoyl chloride to form an ester. Describe what would be observed when the alcohol reacts readily with this, and name this mechanism for the reaction that forms the ester, and then draw the structure of it. So first of all, we're reacting ethanol chloride with an ester. So if you are reacting ethanol chloride, you're going to make the ester, but you're going to boot off an HCl. HCl produces misty fumes. You will see misty. The mechanism by which this happens is that we are adding on this alcohol because there's a lone pair in this oxygen, which then bind to the carbon in the acyl chloride here that's deficient, right? It's binding to this carbon that's deficient. So if it's deficient and something's going for it that's deficient and giving it electrons, it's nucleophilic. So we know it's at least that. But at the same time, it's being added on, but it has to boot something else off. So it's nucleophilic addition, elimination, right? Now we're reacting ethanoyl chloride with this to make an ester. So every single ester in the universe will have this structure, C double bond O, O, C in it somewhere, where this part came from the carboxylic acid and that part came from an alcohol, right? So in this sense, what we'll end up having is ethanoyl chloride was a carboxylic acid derivative. So that's going to be your C double bond O bit. So ethanoyl, CH3, it would have been C double bond O, Cl, but that's been booted off. So C double bond O, and then C from the rest of the entire thing. So this point onwards, basically, with this branching off of it. So then it would be C, CH2, CH3, the benzene ring, and then an H there, like that. Remember, that's your ester link. So use the data book to help you answer this question about amino acids. So figure 1 shows parts of 2 polypeptide chains and a beta-pleated sheet. So every single time you see a polypeptide, you also see an amide link, which is always looking like that. Always helpful to know. So then it says the polypeptide chains are held together by hydrogen bonding as shown in figure 1. Explain how these hydrogen bonds form. So hydrogen bonds are where you have hydrogen bonded to nitrogen, oxygen, or fluorine. So what happens is this hydrogen is electron deficient. It's got its, delta plus as well. So electron deficient, therefore it's delta plus, so it's slightly positively charged, which this means it will attract a lone pair of electrons on O, which is delta negative. There's no electron pair donation here. So it says name the type of bond between the polypeptide chains that influences the three-dimensional structure, and then name the type of this structure. So here, we're looking for what's doing that. A different type of bond can form between two polypeptide chains of the chains that contain the amino acid cysteine. Complete the structure to show the bond that forms in the side chain of cysteine molecules. So if I get cysteine real quick, we can see that the amide links have been made, C double bond O and an NH on either side, right? So it's not going to be this. Cysteine here, this is its carbon, that would have been its amine group, that would have been its carboxylic acid group. This is its R group. So here, there's your central carbon, it's got an H on it, that's your amine, that's your carboxylic acid, this is the R group. Something in this R group is telling you that there's a bond, and it's also told you between the side chains as well, so it kind of gives it away. What's happened here is that we've formed a disulfide bridge. So what you end up having is you've got CH2, right? And then you've got an S, which then bonds covalently to another one like this, CH2 like this. It's not dotted lines. They physically are actually bonding with each other like that. So the type of bond in this between the polypeptide chains influences the three-dimensional structure. What is this structure? It is its tertiary structure. Now it says draw the structure of the zwitterion of a dipeptide formed by alanine and serine. So if I go get those two, one sec. So a zwitterion, remember, so if you can see we have an H2N here that's got a lone pair, it can form a bond with an H+. So it can act as a base. Whereas that is an acid. So it can actually lose an H+ to become an acid, CO-, right? Anything in the universe that loses an H+ is an acid. Anything that gains it. So this is a two-step question. We need to form a dipeptide. So that means we're going to have to, first of all, make that peptide link, which is the same as the amide link here, right? And to draw a zwitterion. So amino acids can act as bases because this can accept a proton by forming a data equivalent bond like that. And this can lose a proton and donate it. Anything in the universe that puts out a proton and loses it is an acid. Anything in the universe that gains one like this is a base. So it's a zwitterion of a dipeptide formed by alanine and serine, which is here and here. So we need to make this bond between them and then obviously close off the others. So pick one and then just draw it bit by bit. So CH, CH3, C, and then it would be double bond O next to the NH of this, right? This will also be NH. We'll fill you out in a sec, don't worry. So then it would be C double bond O, NH, make this a bit tidier, NH, and then this whole thing here. So CH, CH2, OH, right? And then C double bond O, OH. Now the thing is though, here it's saying it's a zwitterion. So if it's a zwitterion, what's going to happen is this amine group is going to accept a proton. So I've actually forgotten to draw the other H there. Whoops, it's going to accept a proton. So we actually get another H here, and this becomes a positive because it's got the extra H plus. And this will have lost a proton, given it away because it's an acid to form this. There you go. So now it says use the data booklet to help you answer this question about DNA. Figure 2 shows a fragment of a DNA double helix. The letters A, C, G, and T represent the 4 bases in one strand. The numbers 1, 2, 3, 4, and 5 represent the bases in the complementary strand. So A, C, G, T, C in the complementary bases. It says complete table 4 to show how the correct sequence and bases in the complementary strand are represented by the numbers 1 to 5. So all it is that A goes with T, C goes with G, G goes with C, T goes with A, and then C goes with G. So it'd be T, G, C, A, G. Now it says deduce the total number of hydrogen bonds formed between the 5 bases in each strand. A and T are joined with 2 hydrogen bonds, and then C and G are joined with 3 hydrogen bonds. So therefore, we've got what? 2, 4, and then 3, 6, 9. Which is 13, so it's this one. So base A is a part of nucleotide strand in the DNA shown in figure 2. A nucleotide contains a 2-deoxyribose molecule, and incomplete 2-deoxyribose is shown. Complete the structure to show the nucleotide that contains base A, and you should represent base A by the letter A. So deoxyribose is a pentose sugar, but if you look here, it's 1, 2, 3, 4. It looks like, where's the fifth? The fifth one is up here. We have CH2OH, right? But then we've made a nucleotide, which means it's going to have all of the pieces in it. So all nucleotides are made of a phosphate group, the pentose sugar, and a base. So this OH doesn't actually stay there anymore. What happens is you start getting a link to a phosphate, so it becomes O, P double bond O, and then an O, that's open like this, and then an O minus here. That's your phosphate. We're still not done with the deoxyribose, because the deoxyribose we need to add some hydrogens in there, like this. And then there would have been an OH here, but then because it's gone and bonded off with the next one beneath it, the next phosphate underneath, you'd open the bond there. And then it'd be an H here, and they've told you to use base to represent it with A, so it'd be this. So this question is about amines. The infrared spectra A, B, and C. There's a primary amine, a tertiary amine, and a nitrile, but not necessarily in that order. Here we go. It says give the letter of each compound in the correct box. So what we need to do is we need to go and look for in the datasheet what the peaks are, so I'll go get that. So they've said again that there's a primary amine, a tertiary amine, and a nitrile, right? So if there's one of them's a nitrile, we're going to get that one first. So the nitrile peak is in what 2220 to 2260. So we need to figure out which one that is. So we look through this and see if we can find a peak here. So we can see that there's one at one. So that's like 2200. So maybe this one, possibly. Here there isn't one, and here there isn't one. So that actually has to be the nitrile. So we know that nitrile is A. So now for the amines. A tertiary amine doesn't have any NHs in it, remember, because it's where all of the H's have been replaced by R groups. So in that case, this one corresponds to this peak here, the NH one, which must be, this is the primary amine, so that's going to be a tertiary there, because there's no NHs in that, so that's going to be C, B, A. Now it says there are 3 secondary amines that contain 4 carbons per molecule. Draw the skeletal formula of these 3 secondary amines. So when you've got 4 carbons and you've got an amine, right? So what you can have is an N, and start with the middle and then draw the rest out, right? So it's secondary amine, meaning that 2 of the N's groups have been replaced with with R groups, right? So we've got 4 carbons to divvy up. So it could be an N with like 1, 2, 1, 2, 2 carbons out, or it could be an N with like 1 out there and then 1, 2, 3 on the other side. 1, 2, 3, 1, 2, 3, 3, 1, 2, 3. Yep. Or it could be an N with 1 here and 1 here, and then 2 branches coming off like that. There you go. Primary amines can be prepared by the reaction of halogenoalkanes with ammonia or the reduction of nitriles. Justify the statement that it's better to prepare them from nitriles rather than halogenoalkanes. The problem with using halogenoalkanes, for example, if we have Br and CBr, and we swap it for C and H2, is that there's still a lone pair of electrons there, and for as long as that nitrogen has a lone pair of electrons, it can continue doing more and more nucleophilic substitution, which we don't want, which means you'll get further substitutions and mixture products. So it's better to use a nitrile because you're just going to make one singular thing. You know, there's no further reaction to take place. So that's what I'm going to write. You can have further reactions with halogenoalkanes, or you could say nitriles do not have further reactions. Therefore, you've got a single product, and here you've got a mixture of products. Now it says, draw the structure of a primary amine with 4 carbon atoms that cannot be formed from a nitrile. So in nitriles, what you have is you have C with a triple bond to an N, right? Now, if that's the case, then it would only be possible to exist just, at the end of a carbon chain. So basically what we've got to draw is we've got to draw a carbon with too many things on it so it can't form a triple bond with something. So what I'm going to do is I'm going to start with just drawing a carbon in the middle, and I'm going to just put like methyl groups on it, like so. And then give the last one, because it wants a primary amine, which means it's an NH, but like what? So it would be NH3, but only one of them is swapped with the carbon or R groups. It's going to be NH2 instead. Here, that. Because it's not possible for this to have originally had 3 bonds with the nitrogen. There you go. So student dissolves a few drops of propylamine in 1 centimeter cubed of water in a test tube. Give an equation for the reaction that occurs, and then describe what's observed using indicator when adding to this. So what we need to do is write down what we obviously know. So if we have propylamine, it's going to be CH3, CH2, CH2, NH2, and we're adding H2O. And it's reversible because I know what this is going on, but I'm just going to write that there. But if in doubt, just have a think what's going on. We're adding water to this thing. What's the water going to end up doing? This is an NH2. It's got a lone pair there, and it's ready to give it to an H+. So this can act as a base and accept a proton. So what ends up happening is you get CH3, CH2, CH2, NH3 plus an OH minus. It's acting as a weak base. So because it's a weak base, it's going to turn it blue. Some people are talking about litmus paper and stuff in this. It's not that, and because it won't go like purple because it's what's the word? It's a weak base. Phenylamine can be prepared by a process involving the reduction of nitrobenzene using tin and an excess of hydrochloric acid. Give an equation for the reduction of nitrobenzene to form phenylamine. Use H to represent the reducing agent. Explain why an aqueous solution is obtained in this reduction, even though the phenylamine is insoluble in water. So the equation, first of all, start with the basics. As you know, it's going to be, they've told you we're using nitrobenzene, so it's going to be C6H5NO2, right? They've told you to use H as the reducing agent, so adding this many H. And what do you end up making? Well, they've told you you're going to make phenylamine, right? So that's going to be C6H5NH2. right, plus something else. Now, if you compare them side by side, this N has picked up H's, which is pretty good looking. But here, there's two O's there that have not just completely just not here anymore. So it's most likely if we're adding H and there's O's, you're probably going to make O2, sorry, H2O. And there's two O's, so it's probably going to be two H2O on this side. Then, this can be treated as if you're just adding a singular H, you just need to balance it out like that. So here, we've added 2 extra H's. Here, we've added 4 extra H's. So then 2 plus 4, 6. There you go. Now it says phenyl amine is insoluble in water, but for some reason we get an aqueous solution. Again, there's an NH2 here, which can act as a base and accept an H+. So what can happen is, that can act as a base, accept an H+, and then it can react with this, it can become an ion, like an NH3+, and then it can form a salt with the acid that we've added. And I think they've told us it was what, hydrochloric acid? Yeah. So what happens is you end up getting C6H5NH3+, Cl- salt is present, and that is soluble. There's several isomers with the formula C6H16N2. One isomer is shown. Give the number of peaks of the carbon-13 on mass spectrum, and instead explain the splitting pattern with the peak for the hydrogens labeled in this. So the number of peaks in the carbon-13 spectrum is going to be the number of carbon environments. So start and just work with the way up. So there's 1 here. This one's different to the other one, so there's 2. There's 3, but that's going to be the same as this one, so that's also 3, and then 4, and then 4 there. So we have 4 peaks. And in terms of the splitting pattern, this one here is that here there's no hydrogens on there in order, so that's out. But here it's got 2. So that means it's going to be a triplet. And why? It's because there are 2 hydrogens on the adjacent carbon. Loads of people were just saying, oh, n+1 rule applies. That doesn't show them you understand what the hell that means or what it's going on, why that's the case. You need to explain why. Now it says, draw the structure of the isomer used to make nylon 6,6. So, unfortunately, it's one of those weird ones where you've got to know what it is. Nylon 6,6 is made from 1,6-diaminohexane and hexane dioic acid. However, you can also, sort of figure it out from here because they've told you what its formula is, right? Now, because we are making a polymer, a polyamide, because that's what it is, it's going to be C double bond O NH, right? This must have had an NH2 on either end at some point, or at least one end, but in this case we know it's both ends because there's 2 ends here. So start with your NH2s, and then you should be fine. So H2N, and then there's going to be a bunch of carbons in between, 6 of them. So there's going to be CH2 times 6, and then there's going to be an NH2 on the other end as well. The reason I know is because I'm making an amide link. I also know that there's 2 ends here. It's most likely going to be 2 amino groups on either side, so diamine or something. And also it is 1,6-diaminohexane. You do need to know that for this. Now it says, draw the structure of the isomer of this that contains 2 primary amine groups and only has 2 peaks in its carbon-13 NMR spectrum. So that means if it's only got 2 peaks, then a lot of these carbons are going to have to end up being identical. Now, if it's got 2 primary amine groups, draw that first, right? So we know that on one end it's going to have H2N. I'm going to try my luck and see if I just put a carbon and a carbon here, and then an H2, right? Now, if you only want 2 peaks at its carbon-13 NMR spectrum, this in itself and this are going to give you 1. They're both identical. So we need to figure out what to do with the other 4 carbons so that they are all in the same peak, environment, so they all give 1 peak. If I put CH3s around this, that fits the bill. These are all in the same carbon environment. That's 1, 1, 1, 1. These are two separate to these, but they're both in the same carbon environment too, so there's 2 peaks. There you go. Now it says, draw the structure of the isomer of this that contains 2 tertiary amine groups that only has 2 peaks. So again, start with the group and then the rest falls into place. If it's tertiary, then I know there's going to be N with a C and a C and a C, right? So that's 1, 2, 3 used up. The other carbon is also tertiary amine, so it's probably going to be this. Because if you have a tertiary amine, primary amine is where you've got 1 carbon or R group. Secondary is this, tertiary is this, and then quaternary is this, quaternary ammonium ion. So here, that's the only thing I can think of that would probably give us 2 peaks. And if we have a look, if I just fill out the rest, so CH3, CH3, CH2, CH2, CH3, CH3. There's 1 carbon environment, that's the same. It's the same as this, that's the same, 2, 2. There you go. Anyway, I hope that helps. Please like and share and subscribe, you know the drill, and thank you very much.